Thank you very much for the introduction. My name is David Sawyer, co-founder and chief product officer at Deeplite, a Montreal-based software startup dedicated to making deep neural networks faster, smaller, and more energy efficient. We're very excited today to show you at the Embedded Vision Summit a technology demo of our flagship software, Deeplite Neutrino, an automated, flexible software that helps AI experts easily create highly compact, highly compressed neural networks based off of their pre-trained networks that meet target resource constraints for production. So let's dive into it. As was mentioned, we focus on optimizing DNNs themselves to meet a number of objectives, and this is really across multiple verticals. And as we'll see in the demo, we do focus on specifically fully connected NLP models, or really CNNs and convolutional neural networks. So in the demo, we're going to show how we can take our software, which is available on GitHub. We'll talk about in a little bit the community version as well, but how we can easily take this software, optimize these models, and make more compact versions of them. So let's dive into it. As you can see from the Deeplite Neutrino software here, it's very easy to install, it's very easy to get set up, and we can achieve pretty meaningful reductions in both the memory footprint, the resource demands, parameter counts of many standard neural networks used for standard computer vision tasks. We do have a community version available, as you can see from the GitHub here, which is freely available and anyone can sign up to start using it right away. We definitely look forward to your feedback on it. To install the software, it's pretty simple. You could be using either your desktop machine, a virtual machine, or a GPU-enabled device is recommended to simply install the Python library or pip package onto your machine using, right now, the PyTorch AI framework. We do have a TensorFlow version coming soon, but in this demo, we're going to focus on PyTorch. And the installation right here, you can see, very simple. So once the software is installed, we want to get up and running and optimize the neural network. We do have a Docker image coming as well to complement the pip package from PyPy. We be available on Docker Hub, and we do provide the Docker image right now to our production customers as well, if you're curious about that. But fairly straightforward to use the zoo. We do provide a model zoo as well that goes along with this optimization software. And upgrade and uninstall, very straightforward to do. So how you can imagine this works, it really has three inputs. You have your train and test data for the model that you've trained, your pre-trained model, so mainly CNN models in this case. We are getting into transformers in the future, that's exciting. We're going to focus on CNNs for today. And then the last piece, which is really important here and is really cool, are the user constraints. So the user constraints are things like the acceptable accuracy for your deployment. How much accuracy can you trade off? Do you have any accuracy you can trade off in your pre-trained model? And that will affect, the level of optimization you can achieve. Of course, the compression rate itself, that's something really cool that we can control and throttle to try and find the most optimal trade-offs that we need to make when we're taking these models and making them targeted for inference and production deployment. And then handing off these three inputs, the constraints, the model, the data set to Neutrino, then asking Neutrino to run a different mode or the preferable mode for this optimization to produce an optimized model that can then be taken, deployed across the millions and billions of devices that are out there on the edge. So as was mentioned, right now focusing on the PyTorch framework, very cool, very powerful framework for training deep neural networks, very popular too. We definitely have some work on TensorFlow going on as well, and have done a number of cases there. But PyTorch we're going to focus on in this example. And so the first part here, you can either take a standard data set for testing or your own custom data set with custom data loaders as well. That's totally possible. That's the first input here with your train and test splits. Next, you'll choose a model. So it could be your own pre-trained model, custom model, could be a standard model, could be a model from the Deeplite zoo as well. And then you take these two inputs and hand them to the optimization engine. This is the cool part here. We're going to show from the documentation the different controls you have as a user. And then shortly after this, we're going to get into a video that basically shows end-to-end how in one line of code, everything we're talking about here can be actuated and achieved to basically, in a matter of hours, replace the weeks, if not months of trial and error. So that's what's happening right here. First, you have your delta, so that's the accuracy criteria we mentioned earlier. How much accuracy, if any, can you trade off? Next, you choose your optimization mode. This can be compression or latency. So compression, you can think of it like you have a very large workload, very large model. You want to run on a microcontroller, so you need to compress it to meet the memory constraints of that microcontroller, for example. Latency is more like if you're running on a GPU or a TPU instead of maybe like a CPU, for example, but you would also like to increase either the throughput or reaction time, reduce the prediction time of your model. So latency mode is really useful when we want to achieve these kinds of things with our workload. To complement delta and optimization, we have what are called level and deep search. These are both functions that allow us to kind of throttle, again, how long the optimization takes, because there is some retraining here, but that'll affect how great the result could be. So basically, the simple intuition is the longer you let the optimization run, the better the result can be. And so while level 1 will be faster than level 3 can get us a more compressed model. And then deep search, which is kind of cool, initiates a secondary level of search, where we want to take a great result from the first step and then refine it a little bit further to meet our criteria. The process will be longer, but we'll get a better result. And that's the idea here. So in addition to all these functions, we do have other capabilities and methods to change the precision, for example, if you dispatch norm layers. Horvath is kind of neat so that we can run the optimization on multiple machines at a time. That's in our production version. So that's really useful to speed up jobs, or if you have more compute infrastructure to take advantage of that when we're optimizing our models. And then at the end, we get our output here as a PyTorch or ONX model. So let's wrap all this up into the video we mentioned earlier on how we can actually take all the stuff we talked about and make it happen. So really cool here, everything we talked about earlier from the code, we're going to see it all come down into one line where we basically say, here's the model we want to optimize, here's the data set we want to optimize, here's how we want to optimize it, and then ask Neutrino to do that for us. So data set, model, the other controls we talked about earlier. And as a user, you basically press run. When we press run, here's what's happening. The engine is going to first profile the model. It's going to say, okay, what's in it? What do you need me to do? What's the acceptable accuracy criteria? And then it's going to initiate its search. It is going to also estimate for us how long it thinks the search is going to take. And as you see here, we had a less than 1% reduction in accuracy, a 28x reduction in model size, and that's in full precision. So from 76 megabytes to 2.7 megabytes, if we quantize this with simple int8 quantization, we could have a less than 1 megabyte model. The memory footprint is reduced by 12x and MAC reduced by 5. This all happened in less than 3 hours. The results are super exciting. You can find these on GitHub in our academic papers as well. We'd love to get your thoughts on them. And again, we invite you to try out the community version we just showed you. Thank you very much for joining our demo today. We really look forward to your feedback and look forward to the Q&A session. Thank you very much, everyone.